We're going to start our study of integration by considering some basic facts about integrals. We're going to assume we have some function f that's defined on a domain capital D. F is going to be continuous on D except perhaps at a finite number of points. Technically, you can relax that condition and you can let the function be discontinuous at a countable number of points. However, the sort of functions we're going to be working with, like probability density functions, we generally don't really have any problem like that. So that's not going to be a major consideration for us. And what we're going to do is we're going to focus on two different forms that the integral can have: the definite integral and the indefinite integral. So first I want to talk about the definite integral of the function f on the interval a, b. So we're going to assume that we have some bounded open interval a, b, and we're going to say that the definite integral of f on a, b is basically the area between the graph of the function and the x-axis. However, you notice that there's a little caveat that we have to add, which is that the areas we're going to be considering are what are sometimes called signed areas. In other words, a signed area is an area that has a magnitude of the area we're considering, but it also has a sign associated with it. So portions of the graph above the x-axis are going to be considered positive in sign. Those below the x-axis are going to have a negative sign. And so you can see that the area, using this definition of the integral, is going to be this positive area, this yellow positive area, minus this blue area. Okay. Now, defining a definite integral as an area in this sense has some important consequences. There are some direct consequences from this definition. The first is that if we integrate a function from a point to the same point, we're going to get 0. And the reason why is because, remember, an integral is an area, so we have no area for this particular sort of graph of the function, right? This is just a straight line. Notice how I'm writing the integral also. Sometimes we drop the argument of the function and the differential dx, okay? The second consequence is if we interchange the order of the endpoints, the sign of the interval changes. And that's a direct consequence of the first fact we have here. The second thing, which is what we would expect for an area, is that areas scale linearly with respect to one dimension. In other words, if I have an area in 2 dimensions and I multiply one of the dimensions by a scalar constant, the area should also increase by that same scalar. And we see that. We see that the integral of a scalar, k, times a function is equal to that scalar k times the integral of the function. Another consequence of the integral is because areas are additive. Therefore, if we add a point c, we can basically break the integral up like this. Notice c does not have to be between a and b, by the way. Okay. And the last consequence is that because areas under curves also are additive, the integral of the sum of two functions is the sum of their integral, provided that f and g are both integrable. So that gives us pretty much the rules that we need for manipulating definite integrals, and also gives us an idea as to what they are. But now we want to shift gears and we want to consider a different form for the integral called the indefinite integral. And what I want to do is I want to start off with a very important theorem. This is called the Fundamental Theorem of Calculus for the derivatives of integrals. And the statement of the theorem is as shown. If we take the derivative with respect to x of the integral from a to x of f of t dt, notice that x is a limit of integration. Okay, notice that we do not have x in the integrand. Okay, we use t. And so very often the variable of integration, as it's called, in other words, the variable that occurs in the integrand, is called a dummy variable. We can put anything there. But it says that if we take this derivative, we're going to get f of x. Okay. And I want to prove to you why this is so. We can actually use a lot of the things that we've learned up to this point to prove this. So we're going to start off, we're going to define capital F of x to be the integral of f of t dt from a to x. And now we're going to look at the derivative. And this is just using our definition of derivative that we had before. Now notice that this difference, capital F of x plus h minus f of x, is the area under the graph of f from x to x plus h. So this is an actual area. We can sketch this out. And if we suppose that the function is differentiable, we didn't suppose that in the beginning of the proof, but let's just suppose that's true, then we know from Taylor's theorem that we can write f of x plus h as f of x plus f prime of c times h, where c is between x and x plus h. And if we now go to approximate this area using the trapezoid rule, okay, so these can be my endpoints of the trapezoid I'm interested in, okay? I know what the formula is, okay? It's the average of f of x plus h times h. I'm going to substitute in this Taylor series expansion for f of x plus h, okay? And when we go ahead now and we substitute this area for the numerator in the difference quotient and evaluate it, you see what's going to happen. This h will cancel. You'll have one h left. And when you take the limit as h goes to 0, you're going to get f of x. Okay? So this is proving this statement. Now there's a consequence to this theorem. Notice that what we're claiming now is that the derivative of this quantity, which I'm going to write as f of x plus c, because I can only know that quantity up to a constant, since when I take the derivative of the constant it goes to 0, right? So for example, if I tell you that the derivative of a polynomial is x, okay, all you know is that it was x squared divided by 2 plus c. You don't know what that constant is. So I'm going to rewrite it like this. And notice what this tells me now. This tells me that I can write this integral as some function of x, which we call the antiderivative of f. And we call it that because we see that what this is telling us is that the integral basically is an inverse operation with respect to the derivative. That's what makes it the antiderivative. These two operations, in a sense, undo each other. Okay? Plus capital C. That's our constant of integration. And that's going to depend upon the endpoint A. But in general, we're not going to specify that. Okay. So that's our first important theorem. Now, we've just shown that the derivative of an integral gives us back the function. What about the integral of the derivative? We would expect that would also give us back the function too, right? And we're going to prove that. Using this first theorem, we're now going to prove a second theorem, which, as you might guess, is the fundamental theorem for integrals of derivatives. And the statement of this theorem says that if f prime of x is continuous, then the integral of the derivative of the function from a to b is f of b minus f of a. We're going to prove this now. So let's start off by defining a of x as the integral of f prime from a to x. Okay, this is just the area under the graph of f prime from a to x. And I'm going to take the derivative of both sides. Okay. Now the derivative of the right-hand side, by the theorem we just proved, is f prime of x, because we said that f prime was continuous, therefore it satisfies the hypotheses of that theorem, and the derivative will be f prime of x. So this tells us that the derivative of a is equal to the derivative of f, which tells us that a is equal to f up to a constant, right? Now if I put in x equal to a, I notice that capital A of small a is going to be 0, because this is the area under the curve from a to a. But I also know that capital A of a is equal to f of a plus c. So using those two facts, that tells me this constant of integration is going to be minus capital F of a. And that's what I said before, how that constant of integration actually depends upon the lower endpoint. Now you can see that. And now we have that capital A of x is equal to capital F of x minus f of a. I simply let x equal to b and I'm done, because the integral from a to b of capital F prime of x is equal to capital A of b, which is equal to f of b minus f of a. And our proof is done. So hopefully this kind of gives you an overview of the basic properties of integrals we're going to use, and also proves these two facts that we know, but maybe you've never seen proven carefully before. Next, we're going to consider techniques of integration.